Light is an electromagnetic wave consisting of electric and magnetic fields. With the continuous distribution of energy over the region of space it propagates. We have already learnt that the wave theory of light satisfactorily explains the phenomena of interference, diffraction, and polarization. Now, let us apply the wave theory of light to the photoelectric effect. According to the wave theory, when electromagnetic waves are incident on a metal surface, the electrons of the metal surface absorb the energy continuously. Photoelectrons are ejected from the metal surface. If the amplitude of the waves incident on the metal surface increase, the energy of the waves increase, and hence the energy absorbed by the electrons increase. Therefore, as per the wave theory, we observe that the kinetic energy of the ejected photoelectrons increase with increase in the intensity of incident radiation. But photoelectric effect experiments show that as the intensity of the radiation increases, there is no increase in the maximum kinetic energy of the ejected electrons. We learnt earlier that the maximum kinetic energy, Kmax, for the ejected electrons is equal to eV0, where V0 is the stopping potential. This shows that the kinetic energy of the photoelectrons is not dependent on the intensity of radiation, which contradicts the wave theory. Therefore, the experiment shows that the maximum kinetic energy of the ejected electrons is independent of the intensity of the radiation. Further, according to the wave theory, irrespective of the frequency of the radiation of sufficient intensity over a period of time should be able to eject the electron from the metal surface. But photoelectric effect experiments show that for every metal surface, there exists a certain minimum frequency called the threshold frequency of radiation, nu0, required to just eject the electrons from the metal surface irrespective of the intensity of the radiation. This again contradicts the wave theory. According to the wave theory, there is a time delay in the incidence of the radiation on the metal surface and the ejection of the electrons from the metal surface, whereas photoelectric effect experiments show that electron ejection is an instantaneous process when the radiation is incident on the metal. This contradicts the wave theory. From these facts, we can conclude that wave theory fails to explain the experimental results of the photoelectric effect. In 1905, Albert Einstein proposed a radically new theory of electromagnetic radiation to explain the photoelectric effect. This theory addresses the contradictions between particle nature and wave nature of light. According to this theory, electromagnetic radiation energy is built up of discrete units called quanta of energy of radiation. This is also called the photon. Each photon has energy E equal to h nu, where h is Planck's constant and nu is the frequency of the incident radiation. When photons are incident on the metal surface, the electron of the metal absorbs energy from the photon. the minimum energy required for the electron to just escape from the metal surface is called the work function phi naught. If the energy absorbed by the electron is greater than the work function of the metal phi naught, the electron is ejected with maximum kinetic energy Kmax equal to E minus phi naught, where E is the energy of the incident photon. Let this be equation 1. This equation is referred to as Einstein's photoelectric equation. However, the electrons which are more tightly bound emerge with kinetic energy less than Kmax. Since kinetic energy cannot be negative, we have E greater than phi naught for photoelectric emission, and since E is equal to h nu, we have h nu greater than phi naught, or we have nu greater than nu naught, where nu naught is the threshold frequency of the metal equal to phi naught by h. Threshold frequency nu naught is the minimum frequency of the incident radiation required to just cause photoelectric emission from a metal surface. Since nu naught is equal to phi naught by h, we have phi naught equal to h nu naught. Let this be equation 2. Substituting the value of phi naught from equation 2 in equation 1, we have the maximum kinetic energy of ejected electrons Kmax equal to h nu minus h nu naught, since E equal to h nu. From equation 3, we observe that the maximum kinetic energy of the ejected electrons is proportional to the frequency of the incident radiation nu, since h nu naught is constant for a metal surface. From this, we also observe that the maximum kinetic energy of the ejected electrons is independent of the intensity of the incident radiation. As the intensity of the incident radiation increases, the number of photons incident per second on the metal increases. Thereby, the number of electrons absorbing energy from the photons increases per second, and hence the number of electrons ejected per second from the metal surface also increases, thereby causing an increase in the photoelectric current. If V0 is the stopping potential for a certain frequency nu of the incident radiation, the maximum kinetic energy Kmax is equal to EV0. Let this be equation 4. Substituting equation 4 in equation 3, we have EV0 is equal to h nu minus h nu naught. Let this be equation 5. We observe from equation 5 that the stopping potential V0 is dependent on the frequency nu of the incident radiation, since h nu naught is constant for a given metal surface. However, the stopping potential V0 is independent of the intensity of the incident radiation and similar to the maximum kinetic energy. On rearranging the terms in equation 5 as shown, we get equation 6 as shown. Equation 6 is similar to the equation of a straight line y is equal to mx plus c, where the slope m of the graph is equal to h by e. From equation 6, as stopping potential V0 varies in a linear fashion with the incident frequency nu, a graph drawn between the stopping potential V0 taken on the y-axis and the frequency of the incident radiation taken on the x-axis is a straight line. Millikan performed the photoelectric effect experiment for a series of metals and found that the stopping potential V0 varied in a linear fashion with frequency and from the slope of the stopping potential. V0 versus frequency, new graph, determined the value of Planck's constant using the known value of charge on electron, which is equal to 1.6 into 10 power minus 19 Coulomb. The value of Planck's constant h is equal to slope of the graph into the value of charge on E. The value of h is found to be equal to 6.626 into 10 power minus 34 joules second. The intercept on the x-axis provides the value of the threshold frequency nu0. The work function of the given metal surface phi naught is equal to h nu naught can be determined since we know the value of Planck's constant h. Irrespective of the intensity of the radiation, the photoelectric emission is an instantaneous process, as was experimentally verified.